Okay, and so if we want to find it turns out later on, I'm sort of jumping ahead a little bit, but the ratio of the stiffnesses in the y and the z axes is going to be the ratio of those moments of inertia. And so if we look at this formula here, we'd see that they're the same, except that we got WH cubed here, and we have HW here cubed in the other one. So we have WH cubed, HW cubed, and so we get H over W squared. So the ratio of the stiffnesses in the two axes is the square of the aspect ratio. So that means, like, if we have a beam like this that's very tall and narrow, it will be, let's say if this was 10 to 1 aspect ratio, right? 10 times taller than it is wide here, then we have the ratio of the spring constants is different by a factor of 100. So if we think about it in pushing downwards like this, then we'd get a spring constant that's 100 times stiffer than it is pushing sideways like that. And then the opposite is true in this case. So it's 100 times softer in this direction than it is to a z-axis force here. Whereas this beam that has square cross-section has equal spring constant in both the y and the z directions. Okay, so the equation here actually, so going back to this equation here, the one that's in red, this one is fundamental, okay? So it turns out that for any loading condition, we can always solve this equation. It's a matter of finding the bending moment, okay? So that's what we'll do. I'm just going to do a very simple, I guess I have the equation here as well. So this is the equation that's fundamental. It's not very good. Huh. So the example that I'm going to do here is a cantilever with a concentrated load at the tip. Okay, so this is like, if you imagine, for example, if we had a proof mass and it was moving downwards and we had a symmetric problem, well, this is that's what this case is modeling. So first thing we need to do is we need to figure out, there is, like we said before, okay, so there's a point force over here. There is a moment over on this side that has to counteract the twisting of this force because the thing is in equilibrium. And so it turns out that, hopefully you can see pretty easily, that the moment here is going to be equal to F times the length of the cantilever. Okay. And so now what we want to do is we want to find the spring constant. F is equal to K times the displacement. And so what we're going to do is we're going to say that the spring constant K is equal to force over displacement y. Okay. So this is the bending moment at the base of the beam. And it turns out that if we cut the beam anywhere else, we'd find that, let's say that we make a cut over here. Okay. So we could say that this is moment at some point x, okay? So that bending moment is going to be equal to m at x is equal to F times length of the cantilever minus x. And to show that that's right, we could find that moment at x equals 0 is going to be F times L, and the moment at x equals LC is 0, right? So this we know is the bending moment at the base is the force times the length of the cantilever, and clearly if we make this distance infinitesimally small, if we cut this thing right at the force here, then we should get that the bending moment is equal to 0 because the force is acting at 0 lever arm. Okay, so this is the equation for the bending moment at any point x. Okay, and so now what we're going to do is we're going to use that in combination with the bending equation. So we have this equation, d squared y dx squared is equal to 1 over e I z times m. So we could write that as 1 over e I z times f LC minus x. And so hopefully we can see then that y is going to be equal to the second integral of 1 over eiz f LC minus x dx squared. Okay, right? So we have the second derivative of y with respect to x is equal to this formula. And so we're going to have to integrate this equation twice. And integrating twice gives us y of x is equal to f over eiz. Have a factor of 6 down here. 3 LC minus x times x squared. Okay, so this isn't a very hard integral to do. You can do it yourself. This is the deflection equation for the cantilever beam. Okay, so this tells us what the shape of the beam looks like, and you can see that it's a polynomial in x. So it's basically like has a constant in it, and otherwise it looks like something like x squared. We could write it like this: c1 x squared minus c2 x cubed, right? So you can see that this is a polynomial in x. Later on, we're going to do some approximate methods for solving beam equations, and so this is the deflection equation for a beam, and we're going to need this later on when we do the energy method. So in the upcoming lectures, we'll use this function. Now here, what we're interested in is we're interested in the deflection at the tip of the beam, right? So we don't care, we don't need the whole equation for how this thing looks. We only want to know what the deflection is at the end. And so we can plug in y evaluated at LC, and so we get f over 6 ei z times 3 LC minus LC times LC squared, and when we solve that, simplify, we get FLC cubed over 3 eiz. Okay? And the spring constant, K, is F over Y. And so we have F, actually I'll write it like this. That's F times 3 eiz over F times LC cubed. So these F's cancel. And we get K is equal to 3 eiz over the cantilever length cubed. Okay, so this is the spring constant of a cantilever beam. And let's see, I have one more page here. So if we write it down, then we can look at it a little bit more carefully. There's only so many ways you can write it. Well, we know that Iz is WH cubed over 12. And so we can rewrite this K as 3E WH cubed over 12 LC cubed. So we can write it as 1/4 E W H over L cubed. Okay. So we can either think about this as the fundamental equation, right? This is maybe not so useful because it's not so obvious how I relates to the geometry of the beam. This one here, we see how all the parameters go into it. And we can see it basically spring constant is going to be linear with this is normal to the force. Okay, linear with the width, which is the dimension that's normal to the force. So here's how we want to draw the picture. Here's the force that we're talking about, right? This is really y-axis force. And so we have this direction here this is the width, and this is h, okay? And it's basically, it's cubic with h over L. Right, so if I make the beam twice as tall, I get 2 to the third 8 times as stiff. If I make it twice as long, I get 2 to the third softer, so a factor of 8 softer. So it's very sensitive to the height and the length, not so sensitive to the width. All right, so we use combinations of cantilevers to construct springs, and so we can think about, we have the free cantilever, it's the one we solved, and here's where we get the spring constant, right? This is what we wrote down as K, and we can, I'll call it here, this is like the cantilever spring constant. I'm going to go through and solve a couple of these here later, but so this is the one that I derived. If we had what's called a guided cantilever beam, and it turns out that if we look at this formula, so this is sort of a useful summary table, if you look at the spring constant here, you can see that it is 4 times, right, because this one has 4 in the denominator and this one doesn't. We could write this as 4 times the cantilever spring constant. And then if we look at this one here is this guided one in series with another guided cantilever. This is a spring where we're pulling on the end of this second beam, and the other beam is where the anchor is, and this part here is allowed to move. This is what's called a folded cantilever beam, and we'll see these a little bit later. But so you can look and you see, well, there's a factor of 2 in the denominator, and so we could write that this is 2 times the cantilever spring constant. Okay, and I'm going to derive where this one comes from. And the other one, I may derive, or you can figure it out yourself once I tell you how I did it. Okay, so goals for suspension design. Usually what we would like is we want stiffness ratios to be large. We want a 1 degree of freedom structure that moves only, let's say, in the y-axis. Compliance in the x or the z-axis leads to problems, so cross-axis sensitivity in sensors. So if we make an accelerometer and it's a y-axis accelerometer, we want to really be sure that we're measuring only y-axis acceleration, not just the acceleration in any direction. And then we already know about the comb drive instabilities, right? So we can get instabilities if the suspension isn't very stiff. So we usually want to have it be very stiff in the cross axes. There can also be problems with undesirable resonant frequencies. And so usually if we want to have a dominant vibration mode, we want the other vibration modes to be separated in frequencies. We'd like them to be at much higher frequencies. And so that means we need to have higher spring constants for these other modes. And the last thing is we want robustness against residual stress and stress gradients. So folded flexures release most of the residual stress and cancel deflections due to gradients. I've talked a little bit about why that's true. I'm going to derive some of the effects of axial stress in a future lecture, and I'll as we go through some of these flexure designs, I'm going to kind of make some arguments about why they are the way they are.